Hi everybody! Our group consists of Arseni Kalma, it's me, Alina Marchenko, Stav Doolman, and Tamir Khoramian. We're going to do a summary on the article Thermal Covert Channels on Multi-Core Systems. And I'm going to start with a short introduction. So, the field of covert channel attacks ranges from CPUs to virtual machine to network protocols and even radio transmissions. And it's really hyped in the industry and as an academic research field. So, covert channel communications can be split to two parts, overt channels and real covert channels, where overt channels are the transfer of data through intended data containers, such as files or internet protocols which are designed to transfer data. And real covert channels is the transfer of data through unintended and in ways that are not designed to transfer information, such as registers or access times. This makes covert channels much harder to detect in comparison to overt channels. Covert communication channels is focused on two main parts, storage channels and timing channels. Storage channels is the use of shared system storage to communicate, which can be file attributes, CPU registers, or even exceptions. And timing channels is the use of time taken to accomplish the tasks, such as some access time or based on the CPU time. As we all saw in the first assignment, we were even able to crack a password using solely timing attack. Mitigations against those attacks is basically resource partitioning, which can be spatial partitioning or temporal partitioning, where spatial partitioning is the separation of the resource between the users, which means that each user will have its own CPU or its own core and memory, and he won't be able to access different resources, so he won't be able to access different memory or access different core. And temporal partitioning is the separation and partitioning of the time which a user accesses a specific resource, which means that different users can access the same CPU and the same memory, but on different times. So these are the basic two ways to implement resource partitioning. Our new attack will use heat, thermal attack on multi-core systems. So this work will demonstrate the feasibility of this attack, which is the use of different cores on the same CPU to transfer information. The special thing about it that we'll be able to attack even spatial and temporal mitigation ways, even if they are combined. So, even enabling those two ways to mitigate our attack, we'll be able to pass it and be able to transfer data between different processes that use different cores and even on different times. On more details about this attack, Tamir will continue from now on.
Can be seen here, this thermal management in 86 systems. As can be seen here, the application is sitting on top of an operating system and sending to the operating system its commands to be executed. Then the operating system is using the hardware, the processor, in order to process its commands. The processor is made of some cores, and each core can be measured for its heat temperature. And on top of that, the processor can use another hardware resources like chipset, hard disk, network, memory. Apart from the network, each resource can also be measured for heat temperature. So this is our first observation of the CPU heat temperature. In this example, the writers of the article ran RSA decryption in a loop for 100 seconds, and they saw that in intensive application the core is getting really hot. But also when the application is done, we can see that in stop after 100 seconds, the temperature is getting back down to almost 35 degrees. But after the application is stopped and another application is running on the same core, this application can actually measure this 36 degrees after 50 seconds of when the first application has stopped. And actually this can be used to leak information about the previous application which ran on the same core. So this is the first observation. The second observation, we can see that when a core is making some intense application, then its neighbors, which are geographically close to the core, is also getting hot because there is a hot core next to them. And the other cores, in the left graph, we can see that core 3 is making some intense application, and core 2 and core 4, which are next to it, is also getting hotter, and they can actually measure it and potentially leak information about the core number 3. In the right graph, we can see pretty much the same thing, but here we also went further to core 1 and core 5, and see that they also can leak information about the activity of core number 3. So in this research, the writers of the article will use these two observations in order to construct two types of attacks, which will first use the closeness of the cores to each other when a core is getting really hot to leak information, and the second attack will use the same core but in a timeline with a different application which will leak to each other the information.
Experimental setup used in this article based on Intel Xeon CPU server with 2 processors, each one with 8 cores with Linux operation system. They use the CPU set of commands to control each core of the CPU separately on runtime. On one processor, they run operation system, and the other used for running 2 malicious software pieces, one who tries to leak data, aka source, and another one who tries to catch the leaks and steal the data, aka sink. Researchers tried to leak 100 bits of data, credit card credentials for example, with thermal cover channel, overcoming 2 partitioning techniques we discussed before. So, how can we break the special partitioning? Research suggests we can get transmission of a bit of information from core 3 to core 2 by running the following scenario. Source runs CPU-intensive application for amount of time enough to rise the temperature of the core 3 such that the heat propagates and makes a significant rise of temperature of core 2 if it means to transmit a value 1, or stay idle for the same amount of time if it means to transmit the value 0. To get a good result in this experiment, it took about 750 milliseconds to transmit 1 bit, and they do it 10 times for 100 bits to achieve error rate of 11%, which gives us a throughput of 0.33 bits per second. It basically says we can leak the credit card information in 4 minutes only, and it's a pretty good result. For temporal partitioning attack, researchers must use more complicated setup, with 2 malicious pieces of software run on the same CPU core, each in its own time slice one after another. The attack works almost exactly as the previous one, only the heat can be less, because they run on the same core and no propagation needed, so the CPU-intense software can run for less time to achieve the same results. As we can see here, And they go through the same experiment of trying to transmit 100 bits 10 times, and it takes 10 milliseconds per bit transmission with error rate of 7%, and it gives us bitrate of 12.5 bit per second. It says that we can leak credit card information in only 5 seconds this way.
Okay, pretty scary, huh? Let's talk about some countermeasures that can be implemented to avoid that. First, we could try separating the processes we execute both temporally and spatially. As Alina described before, this thermal attack is able to deal with spatial partitioning by measuring the neighbor core and doing some error correction. But if we increase the distance between those cores, the attacker would have a much harder time dealing with it. As you have also seen, temporal partitioning is solvable by measuring the core's idle times. But if we made the core's behavior less predictable by defining some spatial time slices, for example, it would be much more difficult for the attacker to measure these idle times. By now, you might guess that both of these solutions are not optimal in terms of computation and will probably cost us in terms of resources. But what if we completely blocked an application from accessing the thermal sensors? As it will probably solve the problem, it will not always be possible, especially in thermal aware systems where CPU temperature is actually a key feature. Now, it's quite interesting to think whether or not it's possible, just by measuring thermal traces, that an attacker will be able to identify which application is running on another core. Maybe with some clever machine learning models, he could even reveal secret keys in that way. Just think about how scary that is. To sum up, we showed how thermal channels can be exploited to bypass even strong and modern isolation guarantees that rely on spatial and temporal partitioning. And given that the world is going multi-core and green and energy efficient, we should definitely think about how secured our systems really are. Thank you all for listening, and of course, special thanks to the article writers from ETH Zurich. You should definitely check out the original article and all of its results in these URLs. And that's it. Thank you all.